Have you ever stopped to think about what actually powers your phone, your computer, your car, pretty much everything in your life? Well, the answer is this unsung hero of the modern world, the semiconductor. Today, we're going to pull back the curtain and find out what makes them so incredibly special.
So let me just start with this one question. If you had to pick just one single type of material that is the foundation for everything, I mean, from a tiny light on your router to the biggest supercomputers on the planet, what would it be?
Well, the answer isn't a metal like copper, and it's definitely not an insulator like rubber. Nope. It's this really special class of materials that are for electronics kind of just right. They're the Goldilocks material. Okay, let's break this down. You can pretty much sort all materials by how well electricity flows through them. So on one end of the spectrum, you've got conductors. Think copper wire. They let electricity flow super easily. On the complete opposite end, you have insulators, like wood or plastic, that just slam the door on electricity. And right there, smack in the middle, that's our hero, the semiconductor. And, the scale of this difference is just wild. The conductivity of copper is a huge number. We're talking something like 10 million. But dry wood, its conductivity is a decimal with 14 zeros after the decimal point. I mean, that gap is absolutely massive. And semiconductors live right in that giant empty space between the two extremes. So here's the real kicker. Just being in the middle isn't what makes them so magical. The real power, the secret sauce, is that we can change and control their conductivity with incredible precision. And that ability to be tweaked and controlled is the secret behind literally every single electronic device we have today. To really understand how this works, we need to zoom in, way in. We're going to look at the most famous semiconductor of them all, silicon, because the magic really starts at the atomic level.
All right, quick chemistry lesson. I promise it's painless. A silicon atom has 14 electrons, but the only ones we really care about are the 4 electrons in its outermost shell. These are called valence electrons, and trust me, these 4 little guys are the key to this whole story.
So what do these 4 electrons do? Well, when you get a bunch of silicon atoms together, they form this perfect, really stable crystal lattice. Each atom shares its 4 outer electrons with 4 of its neighbors, creating these super strong connections called covalent bonds. It's like everyone is holding hands with their neighbors. Everything's locked in tight. But here's the thing. A perfectly stable crystal where nothing moves is, well, it's kind of useless for conducting electricity. For that to happen, you need charges that can actually move around. We need what are called charge carriers. So how do we get things moving in this perfect crystal? What happens if you just add a little bit of energy? I'm not talking about a lot. Even just the normal heat of a room is enough to start shaking things up. That heat energy makes all the atoms in the crystal start to vibrate and jiggle around. And if an electron gets shaken with just enough energy, it can actually break free from its bond. It escapes and is now free to roam around the crystal. And that gives us our first type of charge carrier, the free electron. It's no longer tied down to one atom. It can wander through the material, carrying its little negative charge with it, and that movement is the beginning of an electrical current. Now, this is where it gets really, really cool. When that electron leaves, it leaves behind an empty spot in the bond, a vacancy. We call this a hole, and it actually behaves like a positive charge. Now think about this. An electron from a neighboring bond can jump into that hole, but when it does, it leaves a new hole where it used to be. So the hole itself appears to move. It's like watching a bubble move up through water. The bubble isn't moving, the water is just moving around it. That's exactly how a hole moves through the crystal. And this is a huge deal. It's one of the biggest differences between a semiconductor and a normal conductor. In a copper wire, current is just electrons moving. That's it. But in a semiconductor like silicon, you have 2 things creating the current: the flow of negative electrons in one direction and the flow of these positive holes in the other. Okay, so pure silicon is interesting, but now we get to the real game changer. We can make it thousands, even millions of times more useful by intentionally messing with it, by adding tiny amounts of impurities. This whole process is called doping. So, doping is basically the art of taking a pure semiconductor, we call that intrinsic, and deliberately sprinkling in a few atoms of another element. This turns it into what's called an extrinsic semiconductor, and it gives us an unbelievable amount of control over how it behaves. And by choosing exactly what kind of impurity to add, this doping process can go in 2 totally different directions. We can create the 2 fundamental building blocks of all electronics. what we call N-type and P-type semiconductors.
First up, let's make some N-type silicon. We start with our pure silicon crystal, and we add an impurity like phosphorus. Now, phosphorus has 5 valence electrons, so when it sits in the silicon crystal, 4 of its electrons form bonds with the silicon neighbors just fine, but that leaves 1 extra electron just hanging out with nowhere to go.
And that extra electron becomes a free electron, all set to carry a current. Since we've created a material that has an excess of negative charge carriers, we call it N-type silicon. N is for negative. See? Simple.
All right, now for the other side of the coin, P-type. To make this, we add an impurity like boron, which only has 3 valence electrons. So when it tries to bond with its 4 silicon neighbors, it's short 1 electron.
That spot where an electron is missing? Well, that's a hole. So by doing this, we've created a material with an excess of positive charge carriers, these holes. And you guessed it, we call this P-type silicon. P is for positive. So let's just recap that really quickly. For N-type, we add an impurity with an extra electron, making electrons the majority carrier. For P-type, we add an impurity that's missing an electron, which creates extra holes, making holes the majority carrier. In one fell swoop, we've engineered 2 brand new materials with totally opposite electrical personalities. And that, right there, is the fundamental takeaway from all of this. Doping is all about control. It lets us dial in the properties of a material to make it behave in a very specific, predictable way. This control is the absolute foundation of every single transistor, chip, and circuit board you've ever seen. So that leaves us with one final, fascinating question. We've gone to all this trouble to create these 2 custom materials, one that's flush with extra electrons and one that's full of extra holes. What in the world do you think happens when we put them together side by side to create a junction? Well, that, my friends, is where the real magic of electronics truly begins.